Thank
Take
you,
care,
everyone.
everybody. Ciao.
Bye.
Fantastic. Hey, thank you everybody for taking the time today. The the goal of today is to just give a little bit of background on IP version 6. Most of us have been working with IP version 4 for a long time. Some of us are already familiar with IPv6, but if you haven't, just like the rest of the Fireside Fridays series, our goal is to fill in gaps, help you understand things that maybe didn't get explained all that well when you first joined a company. So thank you for joining us today. I work with active countermeasures. I help out with minor pieces of development, but I also spend more time working on support and occasional documentation writing and blogs and webcasts from time to time. No prerequisites for the day, but I will let you know that I'm not planning to go back too deep onto what IP version 4 is. You're welcome to ask questions about anything you see in the slides. And if you're looking at some IPv4 packet and can't quite figure out what this field is, you're welcome to ask over in Discord. But this is mostly comparing 6 to 4. We'll talk a little bit about the addresses used in IP version 6, a little bit about multicast and how we talk to multiple systems at the same time, and also some on operating system and application support for IPv6. One of the reasons why IPv6 exists at all is that IP version 4 was running out of addresses. We didn't have enough for all of the systems that were coming on. And so the design went in to say, look, we just can't do this with 2 to the 32nd addresses. We need to have more. So how many are we going to go with? And the answer came back that we're going to work with addresses that are 128 bits long, and that's 16 bytes or 32 hex characters. I've got an example of one partway down the slide, FE80, 40s, 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 DA7F, FD91, EE44, 5297. Got that memorized? No, neither do I. But that's an example of an IPv6 address. And the goal here was to come up with enough addresses that we could make this transition once from IPv4 to IPv6. There's no point in going through all of this pain if 5 years from now or 10 years from now, we have to go through and do it all again. So I'm going to mess up the quote a little bit. I will try to find the actual quote, but it's along the lines of while it wasn't our original goal to give every molecule on the surface of the Earth, land and sea, its own IPv6 address, it turns out we're not that far off. So by choosing something that's 128 bits long, we will not have to do this again. This is a one-time change, and it was amazingly painful, and it continues to be amazingly painful in some places, but we've made the transition to an addressing scheme that will work basically forever. If you look at that long address that's 3 lines up from the bottom of the screen, that's a little bit hard to write. But the nice part is you've got some ways to shorten it. So let me give you the simplest one on the last line of the screen. When you have multiple zeros in an address, you can leave off the leading zeros. So for example, that address that's 3 lines up from the bottom of the screen can be also represented by the address on the last line. FE80 0 0 0 DA7F FD91 E44 5297. But you still got a long block of zeros in the middle, and so it turns out that you can leave off a long string of zeros by replacing it by colon colon. You can only do this once in an address, so you need to pick the longest block of zeros. And so about halfway down the screen, you've also got that same address in the shortest form you can do, which is FE80 colon colon DA7F and so on. All of those three are the same IPv6 address. All right. Let me give you an example of how these look in practice. In this example, I made an SSH connection out to a machine on the internet somewhere, 167.71.97.235 from my internal host 10.0.0.111. And if you look in the middle of this Wireshark screenshot, I've highlighted the IPv4 block. Now, you'll notice that this is a packet coming back from 167.71.97.235 to my laptop, and it's IP version 4. There are a bunch of different fields down the bottom, differentiated services, the IP ID, the flags field, the fragment offset, a whole bunch of things that have to happen, and then the source address and the destination address. So this is the SSH server talking back to me. I haven't shown the TCP or SSH layers. Those basically don't change. And so we just focused on the IP layer itself. Now, when I switch to the next slide, watch that center block where it says IP version 4, and we're going to switch to IP version 6. This is a little bit shorter. There's less stuff put into that IP version 6 header, but you have much longer addresses in the process. So, like the previous slide, this is a packet coming back from the internet to my laptop, and it's coming from source address 2604 blah 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 C001, and it's going to destination address 2601 blah 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 491C. And those are respectively the SSH server and the SSH client machine. Like before, I haven't shown you the TCP or the SSH layers. We're not focused on Ethernet 2. We're not focused on the frame. There's very little that changes in those, if any. There's a slight difference on the Ethernet layer, but not really a big functional one. All that we really care about at the moment is in that IP version 6 header. Okay. So, what are the other changes that happen when you move to IP version 6? Well, first off, the TCP layer's basically the same, as is the UDP layer. They don't change, and that was intentional. You don't want to have to change every program you've ever written to have a custom compiled version that only works with IP version 4 and another compiled version only works with IP version 6. That would be a heck of a lot of pain. We'd rather have just one program that will talk out to an IP version 4 machine or talk out to an IP version 6 machine without any change to the TCP layer or the UDP layer or the application layer or anything else. The only real exception to that statement is the ICMP layer, because remember, ICMP is very tightly tied to the network layer. ICMP does some low-level housekeeping, but it also does things like reply when there's a problem with the network layer. So as you might expect, the different ICMP types and the numbers used for those have changed. I'm not going to go into much detail about that today, but the headers that are used and the different ICMP record types that are available, there's some good RFCs for that. If you go to www.rfc-editor.org, and if somebody could put that into chat, that would be cool. www.rfc-editor.org. This is a great website that has a lot of summaries of the different RFCs that make these up, including a lot that will refer to IP version 6. Thank you, HK. I appreciate it. When you deal with ports, this gets a little bit odd because if you type in the URL of a system, you commonly separate the IP address and the port with a colon. And that doesn't really work when you've got an IP address, which is itself made up of colons, doubly so when you've got something like colon colon stuck in the middle. Well, is that colon 80? Is that part of the address or is that part of the port? How do you tell? So the one thing that gets a little odd is if you're typing in a URL and you're going directly to an IPv6 address, you have to surround the address with a left square bracket and a right square bracket before you put the port number. It's much simpler to go with a host name rather than an IP address. And the IP address, frankly, is just way too long to type. So www.example.com colon 80 works just fine, whether you're connecting to a web server on an IPv4 address or a web server on an IPv6 address. There's no confusion there when you're using a host name. In IP version 4, we have a bunch of addresses that are called reserved or private addresses. The formal name is RFC 1918. So if you go to the link that Herman that I mentioned earlier, that HK put down into Discord, rfc-editor.org, and you look up RFC 1918, that one describes the address blocks that are available for IP version 4. And those are 10 dot anything, 192.168 dot anything, and 172.16 dot anything through 172.31 dot anything. As you're well aware, those are the addresses that you are welcome to use inside your network, and those have to be translated to your legally assigned IPv4 address at your router or gateway or firewall or NAT device, whatever machine is responsible for performing that task. In IPv version 6, the reserved or internal addresses all start with FE80. And this is important because when you're looking at a network interface and you're trying to decide, do I have internet access on IPv6 or not, you need to pay attention to what the addresses start with. I'll show this in just a minute, but I'll just to save a little time. If an address starts with FE80, it can communicate inside your building. It can communicate on that Ethernet link, but it can't communicate with the outside world. So we'll see that in just a minute. The loopback address, the my system address for IP version 4 is called 127.0.0.1. In fact, any address that starts with a 127 can serve that role. On IP version 6, the loopback address is ::1. So you can always reach your own system by saying, for example, ping 6 space ::1, and that will ping your local system that you're sitting on right now. If there's no address assigned on a given interface, you use 0.0.0.0 for IP version 4. On IP version 6, the equivalent is ::. And if you wrote that out, it would be all zeros all the way from left to right. So that's the equivalent. Sorry here. Can I have both? The people that designed IPv6 totally understood that you can't have a statement that says, okay, up through July 31st, 2001, we're going to use IP version 4. And then starting on August 1st, 2004, everyone is switching over to IP version 6, and we can't use IP version 4 anymore. You can't do that. It is totally not possible. It would be hell. So you have to pay attention to how people are going to make the transition from one to the other. And the most straightforward way to do this is to say any network interface can have an IPv4 address, it can have an IPv6 address, and it might in fact have multiple addresses of either or both kinds, so that it's possible to hold an IPv6 conversation some of the time, and you might switch back to IPv4 some of the time. A given laptop will have both kinds of addresses in many cases. My laptop right here, right now, has both IPv6 and IPv4 addresses. And so, as we'll talk about in just a minute, we'll see when given operating systems choose one over the other. You almost, if your operating system supports IPv6 at all, and that basically is every operating system, most interfaces will have an FE80 address assigned to them right off the bat. The laptop creates it for itself. It doesn't have to be assigned that address. Your operating system says, oh, I've got these 3 network interfaces. I'm going to assign 3 FE80 addresses to them. Uh, and that allows the operating system to communicate on those 3 network interfaces with no knowledge of how to reach the internet, no knowledge of even if there is a router in the building. Uh, FE80 is considered how do I talk to the other machines on my network segment. If there is an IPv6 capable router, then you will get a note from that router saying, I'm here. I know how to talk IPv6. Here's the subnet that we are all sitting on. Go ahead and create your own address on that public network. So you'll see what's called a global IPv6 address in just a moment. Here's an example of that. I'm using the ifconfig command. This is available on most operating systems. If you don't have ifconfig, use the command IP space ADDR. If you're on an operating system with a graphical interface like Windows or Mac, you might go up to settings or control panel and look under network settings. You might have to go into advanced to be able to see the individual addresses. But because Linux does this in a text output, I thought this was the easiest way to show it. Now take a look at the addresses that I have for ETH0. The second line for ETH0 says inet space adder, and that's the abbreviation for the IP version 4 address that's assigned to this interface. 167.71.106.69. Underneath that, I have 2 lines for inet6 adder. Now, here's that note I gave you a little earlier. Notice how the second address starts off with FE80. And if you look at the far right of that line, it says scope :link. And that's your hint that this address is only designed to communicate with other machines on that network link or that network segment. So it's not designed to give you enough internet access to actually communicate through routers and out to the internet and get responses back and hold conversations. If you're looking at a network interface and it has an IPv6 address, but that IPv6 address starts off with FE80 and there aren't any others, you probably can't use this interface to communicate with the outside world. Okay. In contrast, on this system, I have a second line called inet6 adder that starts with 2604. That address on the far right, you see it says scope global. And that's good news because that means that the address going from 2604 all the way out to B001 is a network address, an IPv6 address that will allow me to communicate with other systems as a client, as a peer, as a server, whatever I need to do. So you need that scope global to be able to communicate on the internet. I want to show you one other thing. Take a look at the hardware address on that slide. And you'll notice it starts with 5A4263 and it ends with 68457F. You notice something odd about the address down below? That address looks pretty close. The actual IP version 6 address used on this particular system right here looks almost identical to that MAC address assigned to that Ethernet card. And so you have 58, not quite the same, but 584263, and then FFFE, and then 68457F at the end. I'm going to talk about that a little bit more when it comes to privacy, but just pay attention to the fact that this system generated its IP version 6 address from its MAC address, and the two look really close. So hold on just a little bit, and I'm going to talk a little bit more about this when we get to the slide on privacy. The other command to see these addresses, by the way, ifconfig is not installed by default on Linux systems these days. It is installed on other operating systems. The other command to use is IP space ADDR. And all it does, it shows the same information. It just shows it in a slightly different layout. So just like before, ETH0 shows you two INET6 addresses, one starting with 2604 and ending with B001, and one starting with FE80, and those are respectively scope global and scope link. All right, so we've covered ifconfig. I didn't talk about it, but I'm going to back up one slide. You'll notice that the interface LO has an IP address of ::1, and that's the IPv6 address for localhost. So you can use the ping command to ping 127.0.0.1, or you can use the ping 6 command to ping ::1. And either way, you'll be pinging your own laptop. No packets will actually leave the laptop. It's just talking to itself. Okay. So one of the things that comes up is, well, how many addresses do I get for IP version 6? If it isn't already clear, you get more than the single address your ISP gives you for IP version 4. But the question is, how many do I actually get? Well, starting from the top, this slide talks about how many addresses are available. For a regional internet registry like AFRINIC or APNIC, they will get approximately 10 to the 34th addresses. And then they can break, or perhaps as small as 10 to the 32nd addresses. Either way, an immense number of addresses. They dole those out to local internet registries, which might get anywhere from 10 to the 33rd to 10 to the 29th addresses. Individual ISPs get approximately 10 to the 29th, which is a /32. And then they turn around and they break their block up into smaller blocks of /48 through /56, which are respectively 10 to the 24th addresses up to maybe as small as 10 to the 22nd. An individual ISP then turns around to its customers and says, here you go, guys. I'm going to give you probably a /64. It might be a little bit smaller, might be a little bit less. So the customer gets 10 to the 24th through 10 to the 22nd, and then the customer may choose to break that up into smaller internal networks that are, for example, 10 to the 19th addresses. This is an immense number of addresses. You could change your operating system so that it changed IP addresses every single time you made a fresh connection out, and you would still never run out. It's a little bit wasteful, but you've got plenty. The /64 that you are given by default for your own internal use in your building, I could probably come up with maybe 150 devices in this entire building if I turned everything on. I've got 10 to the 19th addresses available to me. Remember, the entire IP version 4 address space, all of it, If it was handed to me and I got to use every single IP version 4 address, that's 10, that's a slash 32. Um, 4 trillion. I haven't done the math. If somebody could put how many addresses there are for IP version 4 just on a calculator, do 2 to the 32nd. I'm handed I'm handed more addresses than that in just by default by my ISP for IP version 6. Is the concept of subnets gone with using IPv6? No, not at all. We absolutely do use subnets. And in fact, on this slide, when we're talking about the different places where IPv6 are handed out from the top down and they keep coming down to individual customers, you keep breaking that block of addresses up into smaller and smaller and smaller blocks before you get to an individual customer. And then when you get to your own network, you can break it down into smaller subnets and have a development block and have a production block and have a block for your kids' usage and so on. But hey, thank you, HK. Yep. So there are 4 billion addresses in IP version 4, all of them. And what my ISP hands me for my own personal use for IP version 6 is 4 billion times 4 billion. Tons of addresses. I have to give credit to the Wikipedia page on IPv6 address down in the general allocation section. I took many of these numbers right from there. They did a good job of summarizing it. It's also a good reference for some of the things that I'm talking about as a second source of information. With IP version 4, there are times when you may want to reach more than one computer at a given time. And so we have what are called broadcast addresses. Now, if I simply want to be lazy and say, look, ping every device on this cable, I don't care whether what address scheme we're using. I don't care whether, these are reserved addresses or real addresses. I just want to ping everything. So I will ping 255.255.255.255, and every machine on that cable will get that packet. Okay. The other way to do it is to ping the broadcast address for this network. So if my network is 192.168.x.y, my broadcast address for that network is 192.168.255.255. Those are great if I just want to be lazy and reach everybody. With IP version 6, one of the goals is to try to reduce the noise involved. So if you look down a little further on the slide, you'll note that there isn't a broadcast address. I can't take that lazy approach and say, I want to reach every computer on my network. Instead, we're going to use multicast. And multicast is a little bit more fine-grained. In IP version 4, I have a range of addresses that start off with 224 and they go up to 239 dot whatever, dot x, dot y, dot z. Those are addresses where if I ping one of those, I'm going to reach a limited set of machines, not all the machines on the network, a limited set. And that's much better than saying, I'm going to ping every machine on this cable indiscriminately. I want them all to give up some processing time to go and react to my request. Instead, I switch over to saying I want a targeted list of machines. So down in IP version 6, we do have multicast, and the address that you use defines where this traffic is going to go. The first multicast address that we care about is FF02::1, and that says all nodes on this cable. FF02::2 is all routers on this cable. And these are well-known addresses that let me limit who's going to read that. I may have a time when I want to send out a note to any machine that's considered a router on this cable, maybe even before I've got a live network address. Well, I can use that multicast address, for example, to send out a packet saying, "Hi, I'm here. Does anybody have IPv6 address? And could you give me an address, please, to use?" That's where that multicast address comes in handy. There isn't enough space on this slide to list all of the ones that are of interest. But if you go back to that Wikipedia page that I mentioned on the previous slide, they do list some of the multicast addresses that are commonly known and what they're used for. You can reach, for example, all DNS servers on your network if you need to go and send out a DNS request to anybody who might be there with DNS service. Where do I get an address? Well, just like IPv4, let me back up. With IPv6, every computer that comes up can automatically create its own internal use only address starting with FE80 without any help whatsoever. You don't need anybody else to give you permission to create your own FE80 address. Now, remember, that doesn't get you out to the internet, but it does at least get you to a point where you can talk to other computers on the cable and then send out multicasts saying, "Hey, can anybody get me something better than this internal only address?" So with IP version 4, you would normally send out a broadcast to a DHCP server. And that server would then come back and say, "Here's the address I want you to use. Here's the subnet for this network. Here's the gateway for this cable," and so on. With IP version 6, you can place a DHCP version 6 request, which is very similar. But the more common way is for some IP version 6 capable router to send out what's called a router advertisement. That includes enough information that when it's sent to other machines on the cable, they can say, "Oh, cool, my Comcast router. It has the ability to talk IPv6. Here's the subnet for our cable. And now and here's the gateway that I should use if I want to go out." And that's enough information for your laptops and your other devices on the network to create their own address and set up IP version 6 networking based on that router advertisement. Do you do address sharing? In IP version 6, sorry, IP version 4, we have to. There's no way we could have gotten this far with a functioning internet without people saying, "I'm going to take all of the machines in this building and they're going to share one legal address going out." Uh, we wouldn't have been able to keep the internet going with IP version 4 without NAT and address sharing. With IP version 6, there isn't. You don't need it. You can give every machine in your building its own IP address. You have trillions, quadrillions, maybe even quintillions of addresses available. There's no reason to do IPv6 address sharing. To see if you have an internet connection, the simplest way in IP version 4 is to use the command ping. So ping space dash C space 3 8.8.8.8 says, "I would like to send out 3 requests to the machine 8.8.8.8. Would you please tell me if it replies or not?" Now, 8.8.8.8 is Google's public DNS server, and it is available. It can be reached by anybody who has an IPv4 address and an internet connection. So if I send off 3 requests and I get 1, 2, or 3 responses back, I know that I have an internet connection because otherwise I would get no reply at all. With IP version 6, there's a slight difference. The command to use is called ping 6. Does exactly the same thing, slightly different structured under the hood, but I'm going to do the same thing with ping 6 space C space 3 space, and then I'm going to put in Google's public DNS server in its IP version 6 form, which is 2001 colon 4860 colon 4860 colon 8888. If I get some replies back, I know that I have a working IPv6 address and I have a working IPv6 connection. So this is how I can tell whether I have a live internet connection for both IPv4 and IPv6. On a given cable, I might have one or the other, or both, or neither. And that helps me troubleshoot whether my connection to the internet is good or bad. Could I mix these? And so the interesting question is, let's say I have an old laptop with an old operating system and it has no clue what IPv version 6 is. But I would like to reach a machine out on the internet that only talks IP version 6. Can I use the IP version 4 address that I have to talk to an IP version 6 machine on the internet by opening up a connection somehow between the two? And the unfortunate answer is no. You have to pick whether you're sending IP version 4 packets or IP version 6 packets. There's no halfway point between them. So if my laptop will only talk IP version 4 and I want to speak to a machine that's only IP version 6, there's no way to hold that conversation. The alternative is to put in a slightly different form of an IPv6 address that goes to an IPv4 target. But you still need IPv6 support on both machines to make it happen. So that alternate address form is colon 8.8.8.8, and that is technically translated to 0 colon 0 colon 0 colon 0 colon 0 colon 8 colon, sorry, 8.8.8.8. It's the communication is still done over IPv6. So that example I used a minute ago of a laptop that only knew how to talk IPv4 still can't use this approach. Your OS still needs to understand IPv6 to make this work. If you've got a circumstance where you've got one type of address and the machine you're talking to has the other type, or you're limited on what addresses are available to you, or your operating system doesn't support it, or an application doesn't know how to support it. The best way to handle that is with a proxy. And I may open, for example, an IP version 4 connection to a web proxy. And I tell that web proxy, I would like you, please, to open up a fresh connection on IPv6 to this IPv6 only machine way out on the internet. And that's the way that you handle communication when you don't have addresses available. There are ISPs in Asia that have no IPv4 addresses at all. So when you connect up with your device at home and you are using their services, you have an IPv6 address, but no IPv4 address at all. And that means if you're trying to reach an IPv4 machine, you have to go through a proxy that knows how to talk both. And then that proxy will send the traffic off in IPv4. Applications. And in this, I'm going to include applications and libraries. Basically, applications know how to talk IP version 6. They don't have a whole lot of work they need to do because remember, the TCP and the UDP layer are the same, and most applications don't particularly care about ICMP. Ping and traceroute are exceptions, but most don't. So if you're sitting down with a program that you've just written, we wrote 10 years ago and it only knew how to talk IPv4, and you're saying, how hard would it be to add IP version 6? It's not hard. You can mostly make the changes in a small amount of time, recompile it, and send it back out again. A couple of minor details about how you listen on ports and so on. We'll see that in just a minute. Ping and Ping 6, we've already talked about. There are also equivalent programs, traceroute for IP version 4 and traceroute 6 for IP version 6. So, but most programs, you just have one program. You don't have to start Firefox for IP version 4 hosts and Firefox 6 for IP version 6 hosts. You just have one program called Firefox. And depending on what address you put into the bar and whether it's IPv4 enabled or IPv6 enabled, that one program knows how to talk both languages and they just work. So why are we at a state where basically every operating system and most applications know how to talk IPv6? Could people have just said, I'm just not really interested. I'm just going to stick with IPv4 because it kind of works for me? Well, the answer is partly because the U.S. Department of Defense made a mandate that said we need all devices to support IP version 4 and IP version 6. Now, that mandate came out a long time ago, and it has been deferred multiple times. And it's even today, if you look at the current wording for that mandate, it says that by September 2025, 80% of all Department of Defense machines will support IP version 6. And they're still working through old devices that are IPv4 only and will never have IPv6 support. But the DoD mandate and the statement that you can't sell things to the DoD unless they know how to talk IPv4 and IP version 6 made a big difference. A lot of vendors probably said, well, we really like that income from the Department of Defense, so I think we'll add IPv6 support. How does that sound? Here's an example of the change that you need to support IPv6 in code. Not everybody's a Python programmer. Not everybody's a programmer. You may have strong opinions about your particular language, but all I was trying to show here is what's the change needed to work with IPv6 instead of IPv4. The version of this program that only talked IPv4 is the same as what's on the screen minus 3 lines. Those 3 lines, if you went to this slide, I can't easily show it to you, but if you went to this slide and you took out the line that said try, and the first line that says server under H equals, and the third line that says accept, that's the IP version 4 only version of this program. The change to allow this program to listen for incoming connections on IPv6 and IPv4 is what's on this slide here. We first attempt to open up that listening socket with IPv6. And the way that the operating system works is when you do that, you automatically get a listening port on IPv4 as well. You get both with one command. In Python, that try and accept pair of lines says, give it a try. If for some reason that fails, if this operating system has no idea what IPv6 is, or it just tries and it crashes, whatever, try again with only IP version 4. And if you look on this slide, it may not be obvious where that happens. That change is in, let's see, 1, 2, 3, 4, 5. Line 5 has AF underscore INET 6 that says, please try to listen on IPv6 first. And then on line 7, it's going to retry that listening socket with AF underscore INET. AF underscore INET is the equivalent of IP version 4. And I had to add this line in because it turns out there was I think one of the Linux flavors does not enable IP version 6 by default. It knows how to talk it. It has all the code to do it, but it doesn't enable it by default. And so when I ran this program on that particular Linux system, it crashed. So what you see on the screen is the end result that says, try to listen on IPv6 first, fall back on IPv4 if you can't. I'm bringing this up to say that the change is not complicated. It's relatively straightforward. For packet capture, most of the tools that you're interested in can very comfortably save both. Because remember, most packet capture tools are basically handed a block of stuff and they save it to disk, or they analyze it, or they show it to screen somehow, or they come up with statistics. Not all of them do, but many do. So when you're looking at an IP version 4 packet, you're going to see the version field very early on in the display. The first nibble, the first thing that shows up in that packet is going to be a hex 4 if it's IP version 4 and a hex 6 for IP version 6. And I'll note down at the bottom, there technically was an IP version 5. It was for streaming audio and video. It wasn't used very much. People figured out that that's not a great way to go and modify the entire IP layer just to handle a particular type of streaming video. So I'm going to switch back a couple of slides and I'm going to show you that block real quick. Just a moment. Let's head back to Wireshark. Da, 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 da. All right. So we don't show you the the IP version 4. Yeah, okay, there we go. Yep. The first line in the middle display, you see how it has 0100 ... equals version 4. That's the first nibble of the IP layer. And then if I switch over to the IP version 6 form, you notice that 0100 changes to 0110, which is binary for 6. So you can very quickly tell if a packet is IP version 4 or version 6 by looking at that first nibble. And in fact, okay, let's go back to our original slides here. Let me catch up. Okay. So when you come to the operating system layer, what do operating systems use? Well, all three major operating systems, Linux, Windows, and Mac OS, and in fact, frankly, FreeBSD, NetBSD, OpenBSD, basically everything that is still supported and available for purchase or download knows how to talk IP version 4 and 6. The operating system does, the libraries that come with the operating system do, they all do. So with Linux, if Linux is going to try to use IP version 6 by default. If that connection fails, it may fall back to IP version 4. Windows, everything from Vista on prefers IP version 6 as well. There's a doc on Microsoft's site on how to turn that back to just 4 if you need to. And Mac OS also prefers IP version 6 if the system to which it's talking has both an A record, an IP version 4 address record, and a quad A record, which is an IP version 6 address record. If I try to connect to www.stearns.org with my web browser, what's going to come back is that that system only has an IP version 4 address. So no matter what my client system is, no matter what my operating system is, that will have to be an IPv4 connection. But for most systems that have both A and quad A records, most operating systems will prefer to use IPv6. If I want to filter out just IPv4 packets, I can use the packet filter IP. If I just want IPv6 packets, I can use the filter IP6. When it comes time to interpret those packets, if I'm looking at TCP or UDP headers, they're the same between IPv4 and IPv6. And as I've already mentioned, ICMP and ICMPv6 are different. So your application will have to spend a little time learning how IPv6 ICMP packets are structured. The IPv6 header doesn't have all the things that IPv4 had. As part of the process of moving from 4 to 6, the goal was to see if we could streamline that header to make it more efficient. So some of the things that showed up in the IPv4 header have been moved out into different headers. So an IPv6 packet might have anywhere from 1 to 3 more layers than an IPv4 packet. When it comes time to set up firewalls, IDSs, network monitors, IPSs, anything that has to do with your network layer, we're going to have to set up both IPv4 and IPv6 security layers. So if you sit down and say, I just wrote this wonderful firewall for IPv4 that protects all of my internal systems, and then you forgot to put in a firewall for IPv6, it's a little bit like putting up a gated fence around your building, but totally forgetting to put up 2 of the walls that would protect you from the outside world and assuming that nobody would ever try to walk through those. You have to set up both. For DNS, as I mentioned before, IPv4 addresses are called A records, and that turns a host name into an IPv4 address. PTR records turn an IPv4 address back into a host name. On IPv6, AAAA records turn a host name into an IPv6 address, and PTR records again turn an IPv6 address back into a host name. So for example, if I want to turn an IPv4 address back into a host name, I can use the command dig space plus short space dash X. X says, treat this as an IP address and give me a host name. And I look up 8.8.4.4, and the answer I get back is, oh yeah, that's dns.google, which is a host name. And it's the equivalent of 4.4.8.8.inaddr.arpa. So you reverse the IP address for the IPv4 address, append inaddr.arpa, look that up, and it comes back and says, oh yeah, that's dns.google. With IPv6, you do the same thing. Dig space plus short space dash X, and then the IPv6 address. And it turns out that 2001:4860:4860:8844 has a host name of dns.google as well. And if you look down at the bottom, it's a slightly different format. You take each individual nibble, you separate them by periods, and you append .ip6.arpa, and then you turn that back into a host name. I talked about this right at the beginning of the presentation when I showed you a MAC address and I showed you an IPv6 address that was constructed from that MAC address. If I take a 6-byte MAC address and I want to turn that into an IPv6 address, this was the old approach. Break up the address in 2 halves, 3 bytes each. Stick in FFFE in the middle. And you're going to make a 1-bit swap on the bit 7, not the highest bit of the entire address, but the next one down. So to turn 112233445566 as a MAC address into an IPv6 address, I'm going to put that with FFFE in the middle and a 1-bit swap and end up with 132233FFFE445566. And I forgot the colon on that. No, I did. No, I got that right. The problem is if I use that address publicly, if that's literally the address that I use to communicate with machines on the internet, the machines on the internet can see, oh, hey, that looks like a MAC address. I can tell what MAC address was being used by this system when it generated that IPv6 address. And it can reverse that process and come up with 112233445566. Does that really matter? Well, it's a little bit of privacy. In our example, I could take the 112233 that I calculated as the server on the internet, and I can look up in a table called the OUI, or Organizational Unit Identifier table, and see who made the network card that Bill's laptop is using. Not a big privacy issue, but if you were able to do this for my laptop this way, you would see that I'm using a MAC address assigned to Apple. And you might reasonably assume that I'm using a MacBook of some kind, or maybe a Mac Mini or some other device. It's a little bit of privacy. So this approach is not commonly used anymore. It should be basically retired by now, but that's really the only privacy issue with how IP version 6 works. That's really a big problem. Now, granted, there are all kinds of privacy issues with communication on the internet, but that's the big difference between IPv4 and IPv6. You won't generally find that in active use anymore. You can take a look at the IPv6 addresses going in and out of your building and say, hey, are any of these guys using that generated approach? If so, I should check on that. I've got references in here. You've got the slides in the Fire content chat. I encourage you to bring them down and take a look at these. Um, there are, we just had a new Malware of the Day blog written by our own Fan Russo, which talks about IPv6 address aliasing. I encourage you to take a look at that. More references there. And what I'm going to do is leave this slide up. We've got just a minute or two more. I'd love to answer some questions. So Keith and Chris have we gotten any questions that have scrolled by so fast that I didn't even see them go by?
Not that I noticed. I think you were actually grabbing quite a few of them, and you may have inadvertently answered some just by speaking. So,
Okay.
so we
Uh,
appreciate that.
That's a nice problem to have. I like that.
Yes, yes.
So I'm going to apologize. If you asked a question earlier and I didn't answer it, would you mind reposting it over in Discord? And I'll give it a try.
Excellent. Yeah, thank you. Yeah, go ahead and post it up in
Kushal, we
Discord.
encourage you to ask questions over in Discord if you're able to. That would be wonderful. Um, this slide, while we're waiting for questions to come in, real quick, if you're going to the talk in 2 weeks, not next week, 2 weeks, on the 28th, that's Chris's talk on packet crafting. The tool that you're going to want to have, tools are NCAT and HPing3. NCAT and NetCat and NC are different names for different flavors of the same tool. We encourage you to use NCAT because it has some advantages over the older NetCat. NCAT is from the Nmap project, and so it's actually a subsidiary of the Nmap project. All right, so I've got at least one question coming in. Does the 6-bone still exist, or is it subsumed into the backbone? I don't believe the 6-bone is still active. Eric, I'm not sure of that answer though, so I'm going to make that I'm about 60% sure. Thank you for the presentation. Hey, you're entirely welcome. Doing an IPv6 ping, is the response different between you don't have an IPv6 connection versus what you're pinging isn't responding? Excellent question. Yes, it will have different answers. It will probably be protocol unavailable if your laptop does not support IPv6 whatsoever, or you have no IPv6 address to use. If the machine isn't responding, it's going to say host unreachable. And those are going to be different error messages that come back from your operating system and library or the remote end router, respectively. Thank you, Cyber 4N6 Pi. There we go. You're entirely welcome, guys. How does ARP work with IPv6? Oh, it's called something different. It is you're using a host. Let's see, it's router advertisement, router query. It's using a host query. No, node query, host query. You're basically doing. I got to tell you, Mag, I'm going to answer that question later. I've got to look up ARP. I, I'm sitting here and I can't think of the answer. So, Mag, would you please come back onto this channel? I'm going to look up the answer and I'm going to put that into this chat in Discord. All right. How do you prioritize IPv4 over IPv6 or vice versa? Kafka for your particular operating system, Mac, Windows, Linux, or something else. Um, the short version is almost all of them will prefer IPv6 if it's possible. They'll fall back on IPv4 if it's not. If that's a problem, if you need to change that, then I've got a couple of references in these slides. Please download the PDF on how you do it on specifically Windows and Mac. And you can go take a look at those pages and they'll say, here's how you could reverse that or disable IPv6. It looks like that might have been it. So thank you everybody for making the time today. I really appreciate it. Keith and Casey, anything else you'd like to add?
I think you really got it all.
Okay.
Yeah. Yeah. And this was very good. Thank you, Bill. And thank you for helping pull me out of my IPv6 resistance. I think it's about time that I give up and recognize that this exists and I just need to deal with it. So
Yeah.
It's kind of unavoidable at this point. You might have
yeah.
been able to avoid it, let's say 30 years ago. It's a
Yeah.
little tougher now.
Yeah.
Little tougher.
Yeah. Yeah. And I'm
Hey,
sure
Yeah.
everything will be fine.
that's right. So thank you to everybody who took part today on Discord and on YouTube. We really appreciate it. How long would it take to scan an IPv6 space? Forever. You probably exceed the heat death of the universe if you tried to do every single one. Do the math at some point of how many machines you could scan in a given second. It's just not possible.
Yeah. Yeah. In fact,
Um,
I think, didn't you say, Bill, that there are actually more atoms on our
on the
planet?
surface of the Earth. Yeah, it's
Yeah.
pretty close to the number of IPv6 addresses.
Yeah.
Yep. It's not possible. So let's go and wrap that up. Quick reminder that there is no Fireside Friday next week. There will be one on the 28th. So make sure you sign up for packet crafting. And it's been a real pleasure. Thanks for joining us today.
Yeah. Thank you, Bill. Thank you,
Thanks,
Casey.
everybody.